Hello everyone, my name is JOCEL L, SORILA, and today I'll be discussing the application of Newton's second law and kinematics in analyzing velocity, acceleration, and forces. First, let's briefly overview Newton's second law. This law states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. This principle is foundational for understanding motion. Kinematics, on the other hand, provides the mathematical tools we need to analyze motion quantitatively, helping us measure how an object's position changes over time. Now, let's cover some key concepts. Forces can be categorized into two types: contact forces, such as friction and tension, which occur when objects are in direct contact, and the second is non-contact forces, like gravitational and electromagnetic forces, which act over distances. Next, we have velocity. Velocity defined as the speed of an object in a specific direction, and acceleration, which is the rate at which an object's velocity changes over time. Moving on to Newton's second law, which can be expressed with the formula F equals ma. Here, F represents the net force measured in newtons, m is the mass in kilograms, and a is the acceleration in meters per second squared. This equation tells us that if we increase the force acting of an object while keeping its mass constant, the object will experience greater acceleration. In kinematics, we use several K equations to describe motion. V equals U plus AT helps us determine final velocity based on initial velocity and acceleration. S equals UT plus 1 half AT squared allows us to calculate displacement over time. V squared equals U squared plus A plus 2 AS relates final and initial velocities to acceleration and displacement. S represents displacement, U is the initial velocity, V is the final velocity, and A is acceleration, and T is time. Let's look at an example. A 5 kilogram block sliding down a surface with friction. The forces acting on the block include its weight, calculated as milligrams, which equals 49.05 N, and the normal force acting perpendicular to the surface, along with the frictional force. For this example, we'll assume a coefficient of friction of 0.2. Calculating the frictional force gives us F friction of equals U times N, which equals 9.81 N. Next, we find the net force by subtracting the frictional force from the weight. F net equals mg. F friction resulting in 39.24 N. To determine the acceleration, we use A equals F net m, yielding an acceleration of 7.85 meters squared. Finally, we can find the final velocity using V equals U plus AT, assuming the block starts from the rest. Now, let's consider a second example involving projectile motion. Imagine a ball thrown upwards with an initial velocity of 15 meters seconds. The only force acting on it is gravity, which pulls it downward. We can calculate the time of flight using the formula V equals U minus GT to find when the velocity reaches zero at the peak of its trajectory. To find the maximum height, we use S equals UT minus 1 half GT squared. Finally, we can determine the final velocity on descent using V equals U plus AT considering the downward direction. Next, let's differentiate between contact and non-contact forces. Contact forces like friction and tension have direct influence on motion through physical contact. In contrast, non-contact forces, such as gravity and magnetic forces, can affect motion over a distance. Contact forces often result in resistance, while non-contact forces can either accelerate or decelerate objects without direct interaction. In conclusion, we've illustrated how Newton's second law and kinematic equations apply to various scenarios, demonstrating their practical utility in predicting motion. These principles are vital in fields such as engineering, sports science, and vehicle dynamics. That's all. Thank you for watching. I'd like to open the floor for any questions or clarifications regarding the concepts we discussed today.